recording, and uh, so let us start uh, let me share my screen and let us start. Let me close this. Don't need this. Yeah, let us start our. Right. So when we launch our, uh, okay, you you will see that window like this opens up. Okay, I am assuming you have installed R&R Studio. Okay, and this is people who are familiar with R Studio. We see that there are these windows. This window on the top right side has the is called as the environment. Uh, you can say window where we will see all the variables that we create. This is on the left side. This is the console where we will be running all our commands. The right side has different windows here: files, plots, packages, help. All of these things are visible here. So the first thing that we will do in when we launch R is we set our working directory. So you go to session and set working directory and choose directory. Okay, this is we are setting the path of the folder. So I have kept all the files on my desktop folder MLM, and then data and R scripts. Okay, within data and R scripts, we are going to work in multi-level folder. So I select multi-level folder, make it my current working directory, select that folder, double click, you see the name has come, and then click open. You would see it says set working directory. This command has run, and it has now set this as its current folder, and you would see all the scripts are coming here, and we will go to school.r. This is the R script where I have written all the commands. So we will be using this script for running our analysis on the school data that we have just seen. Okay, if I open the SPSS view of the data, okay, if you go to variable view, you see this is all the variables that we had. Okay, if I compare this with that page where we had the variables, let me just show it to you. So we had school code, RID, ID, female, SES, FEM, SES, math, SES mean, Pro 4 year, and public. Okay. For the time being, we are assuming that these variables are already created. Okay. I will teach you how to aggregate also. So how can we create SES mean? Okay. We'll do that later, but we are assuming at the moment that I have the school code. Okay, RID, ID, female, gender, SES, socioeconomic status, the product of FE, female, and SES, math, which is our DB, SES mean, Pro 4 year, and public, right? Again, if we open this and we can just place it side by side to our not this one. Okay, it is. Where is it gone?
So this is school file or the school restructured?
School.sav.
Okay.
School.sav. You see school.sav in the folder, in the multi-level data art scripts multi-level, it is school.sav. School.sav. School.csv also has the same data. Okay, school code RID, ID, F female, SES, FEM, SES, math, SES mean, Prof 4 year and public. So this CSV file also has the same data. Then uh,
Sir, I'm sorry, but can you again, can you please again show the how to import the file like in the Art Studio? Like,
yes, I will do that. Okay, so all of you, you have this data. At least you have the data files with you. Anybody who does not have it, everybody have all these files, right? So school.csv, school.jpg is nothing but the photo of the all these variables, just for people, in case people don't have access to the book, I have kept this photo there. Okay, and then the school.r is the R script that we are now going to run in the R environment. Okay, school.sav is this data file that I have opened. Okay, now just read this data in SPSS, and you can see, I just want to show you how the data is structured, how you have to, if you are doing your own research, how will you actually create the data file. So you see school code, so it says this is school 1, then there is school 2, then there is school 3, and if you go down you will go up till 419. So if I take you down right till the end, you will see there are 419 schools. 419 schools. Okay, then if you see, let us go back to the top again. So this is school 1. Now RID. So student 1, student 2. So this is I basically. I, this is J. School code is J, RID is I. So IJ. So student 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 students are nested in school 1. Then you have 13 students in school number 2. Then you have how many? You have 18 students in school number 3, right? Then school number 4 has 17 students, and so on. Okay, ID is some unique identifier. We don't have to bother about it. It, for all those 6,700, all those numbers, students, they have given some identifier. Then this is student gender. Now you see this will vary even between students. So in school number 1, you can see there are 1, 2, 3, 4, 5, 6. There are 6 females and there are 6 males, or 6 girls and 6 boys. Then socioeconomic status. This is different for every student because it's a individual level variable. Then FEM SES, you see it is nothing but a product of female and SES. So 1 into 0.59 is 0.59, 1 into zero point 0.3 is 0.3, 1 into minus 0.54 is minus 0.54, 0 into zero point 0.85 is 0. Okay, then this is your mathematics score, mathematics performance, maths performance. Then SES mean. Now you see this is a school level variable which is nothing but the mean of all these individual level values. All these. Okay. So if you take the average, it will give us this minus 0.27. This is pro 4-year college 0.08. What does it mean? 8% of these 12 students want to study in a 4-year 8 sorry not these 12 students, 8% of the students studying in the school, 8% students studying in school 1 are opting for or want to study in a 4-year college, and this is 0, that means it is not a public school. Similarly, this is 0, then you may have some, yeah, you have some private school so also, or public school also, so this is 1. So these are school level variables. Any question here, anybody? So this is how you will have to structure your data also. You will need, if you want to, please understand very carefully, if you want to do multi-level analysis, you will have to create these two identifiers. You call them RID or school code, or you call them I and J, doesn't matter. But you will need these unique identifier for each school, and within each school you need a unique identifier numbered 1 to 12. Any questions here? Is this okay?
So just one question here,
Yeah.
the ID that is there, which is the sort
Yes.
of a primary key for them, is that also going to be used in the
No, it
analysis?
is not. It is not.
Okay.
We will only, that is why I said you will need only RID and school code.
Right.
This is just, they, while you were
Sure.
collecting data, you had given these identifiers. For our analysis, we will use only school code and RID.
And sir,
Got it.
ACS, individual ACS mean all are Z score, no?
All are,
Standardized.
yes,
Standardized ones.
these are Z scores. These are Z scores, and this is nothing but an average of these Z
Average
scores.
of it. Yeah.
These Z scores.
So can we take only average?
Can we take?
Average, mean only. ACS, there is no like why to take a Z score? Can we take a mean of
It is up to you. You are saying instead of Z score, you
is it
take a
okay?
mean. It is okay. It is, see, that is about variable construction,
Okay, okay.
measurement issue.
Yes, yes,
How you
yes.
want to, and whether that is considered to be a right method in the literature that you are working.
Okay, okay.
So every literature may, that is about measurement, right, Deepak? How
Yes, yes, sir.
you create variable, that goes into validity issue, whether that is the right way to measure the variable. So I'm not going into that because that's
Yes.
not the focus. We are saying if this is a variable, then we can create this mean also. And how do you do it? You can actually say, if you, in SPSS, there is an aggregate function. Okay, you go to aggregate, okay, and then what is the breaking variable? The breaking variable is the school code, so you bring in break variable. Okay, and what is the summary variable? We want summary of SES, so it says summary. Now you see, we want the summary, so by default actually it, the by default the function is a mean, so we can change this also. We say mean. Okay, you can decide median, you can decide sum, you can decide standard deviation, whatever you want to do. Okay, so summary statistic, we want to do the mean, so you do continue, and then you change the name and the, because mean is already there, let us say, yeah, let us call it as SES mean 1, so that you can see that it is the same variable, the values are the same, so you say continue. Okay, and it says add aggregated variable to active data set, yes. Okay, and then you paste it in a syntax. So I will save this so that we know what is it that we are doing in a syntax file. So I say creating aggregate SES mean. Okay, this is the command, and when I run this now, when you run this, you see it has run and it has created a variable. SES mean, and you can compare what was given to us, we have actually computed. So if you have a variable, it is very simple to create a school level variable or a level 2 variable. So we have created a mean of all these SES. Then similarly 0.68, let us check with, yeah, we are getting the same value, 0.68. Then minus 0.55, we are getting the same value. Is this okay? How we can create it? You just simply go to data and aggregate, and whatever will, this is the level 2 level 2 or grouping variable, and then whatever variable. So math also we can say math. So we want to bring in math, but this will become the mean of all students. So it will create a math mean also. If you say okay, okay, and yeah, okay, SES mean is already there. I say overwrite, and now it has again, now you have a math mean also. It has taken the mean of all these values, right? So very simple. It is very easy to create these aggregate or school level or group level variables. Okay. Yes, now let us come to our studio, and I will show you tomorrow. I'll show you how to do the same in aggregate it in R as well. Okay.
Sir, can you again please show the how? What did you do to import the data?
In
R Studio.
in our studio. So when we launched R, okay, let me close my R again, and let me show you what I did. So I launched R Studio. Right? Then the first step I was telling you is you have to go to session and set working directory, and then choose directory. Okay, and there go to the folder where you have saved. So I have kept it on my desktop, MLM, then data and our scripts. Within that, multi-level. Right? I double click on multi-level, the folder is selected, and I select open. Okay, so I have
Got it, sir.
set my working directory. It is called as setting the working directory. And then now you will see all the files that are there in this working directory are visible. So I click on school.r. That is the R script that we are going to work with. Is this okay?
Yes, sir.
Okay, so now the package that we will be using is called as multi-level. This is the package which has all the necessary commands that are needed to run multi-level model in our environment. Okay, that is the kind of package. So in R, essentially it's a free software, so all variables are all functions relevant to or associated with a particular analysis are stored in a package. Okay, so we invoke this package. So what we do is we have to install. So I will go and say go to tools. First you have to install package. Okay, and type multi-level. Okay, and you see multi-level is selected. Select that and click on install dependencies. That is fine, and install.
Sir, only multi-level, right?
Yes. Yes, foreign is actually already installed. Foreign is always already installed. So we just run line number 2. So it says install packages multi-level, and now line number 2, we to run a command in R, just bring the cursor to this line, anywhere in this line, middle, start, end, anywhere, and control and enter, or you can simply run, click on run here. You see it says run the current line or selection, control plus enter. So library foreign is invoked, library multi-level is also invoked. Okay, so now I have all the functions available for me to read. Line number 5 is basically reading the CSV file. So I say the command is very simple, read.table, then the file name, separator is a comma because it's a CSV, comma separated version, and header is equal to true, mean that the variables. So if I open school.csv, header is equal to true. That means the names of the variables can be found in the header. That is what it means. Header is true. That means read all the variable names from the first line of the file, which is called as header. Now you see, as soon as we run this line, there is, you can see another data frame, or you can say a data set named school is available, because we had read this file and saved it in a data frame or a data set with the name school. So if I click on this school, you see you will get exactly the same data that we were seeing in SPSS. So you have the school code, okay, lines 1 to 12, school code is 1, RID 1 to 12, okay, then you have gender, SES, FEM, SES, then you have math, then the product, the mean of the SES, then Prof 4-year and public. Okay, so our data is run. You can names, just tell us what are the names we have already seen. So it says these are the names that are available. Okay, now tell me everybody, is this okay? Anybody who has not been able to do this? Can I proceed? Is this okay? Fine?
Yes, sir. Thank you.
Okay. Now what is the first? Okay, now this is important. Let us look at the syntax, right? So let me open my window, the whiteboard, and let us look at the syntax. Let us understand how we write the syntax in R. So we are doing the null model. And what had we said in the null model? We had said that Yij is equal to, or let me not write now, you know what we are saying. So let's write in terms of our variables. Math Ij is equal to beta 0j plus Rij, which is equal to gamma 00 plus U0j plus Rij. Right? So what are the fixed effects? This is one fixed effect, and there are two random effects. So the command in R is very simple. It says linear mixed effects model. That's the name of the function, linear mixed effects. and it says, what does it say? Math, which is our y, is regressed on. So the command is fixed effects, comma, random effects. That is how we write it. So what are the fixed effects? Math is regressed on 1, because you can say gamma 0 0, which is intercept, is nothing but the coefficient of 1, right? So we say math is regressed on 1. And then random effect, the syntax is random is equal to tilde. Okay, and what is the random effect? There is one random effect, so we can again say u0j is nothing but the random effect associated with the intercept. So we say random is equal to tilde 1. Rij we don't write because it is already it is obvious that the residual of the regression will always be computed. So this Rij, there is no need. You just have to say random is equal to tilde 1, and then very simple, data is equal to school. That's it. This is as simple as it can get. There is a fixed effect and there is a random effect. That is why I was telling you right from the beginning that we must learn to write the equations, because these equations will help us write the commands that we want to give. So
Sir,
math,
in the fixed effect, there is no equal to in random effect. Why there is a equal to? So
that
like,
is
is
just
there?
a, so in R, this tilde is a symbol of regression.
Okay.
Okay, and this equal to tilde is Pratik, we just have to say this is the kind of a syntax. It has nothing specific about the way we write. This is the way the syntax has been written for this function. That's it. We
Okay, sir.
just have
Okay.
to remember that.
Okay, sir.
So let's go back to our R script and see what have I written. So we say LME, math regressed on 1, random is equal to 1, and yes, what is important is it varies. So when I say that there is a random effect, it varies per what? It varies for school code. So there is a school code. This is the grouping variable. So we can say that you have to write that my u0j, this will vary for every school. So that is something that we have to tell the software, that what should you take as the school code or the grouping variable. This is the variable that will tell us that this u0j changes for every school, right? Which is very obvious and intuitive. That is what we are telling. That is again the syntax, how we declare it in our model. So we simply say math regressed on 1, random is equal to tilde 1, and it varies. So you can say we read this as varies for every school. Data is our school. Okay, this you just don't have to worry. This is just some optimization, so you can always keep it. You remove it also, that doesn't, it's just a fitting function, but this is something that you will have to change for your own data. You will have to change these variable names as per the data file that you have. Okay, so that is something that we want to
So,
run. Yes,
so just to understand the syntax, when we say that math regresses on 1, does that mean that there is
only an
so
intercept.
only one
No,
effect?
there is only an intercept. That's it.
Only one.
That is
Okay,
how you
okay,
read it. Because
okay.
see, what is an intercept? The intercept, you can say, is nothing but the coefficient of 1, right?
Yes. Yeah. Okay. Okay.
That is why we do. How do you tell the software that there should be an intercept? You say regress it on 1, and whatever is the coefficient of 1 is my gamma 0, 0.
And we write here math because math is our y.
Math is our dv. Yeah, yeah,
Yeah. Okay.
absolutely.
Got it. Yeah.
Absolutely. Math is our dv. Is that okay? Okay.
Yes, sir. Clear, sir.
Now we do. So we run this line number 8. Okay. Our model has run. The output is stored in this. You can give it any name. I have, for our understanding, I have given this a name, null dot model. And then when I do summary, okay, you see, if I do summary, this is the output that I get. Now do summary, and please let me know if anybody is not getting the output. Then I will tell you how to interpret the output. But everybody is getting the output. Please see.
Yes, sir.
Yeah, everyone. Okay. Now let's see. Let's read the output. It says linear mixed effects model fit by REML. REML means restricted maximum likelihood. It is okay. Ignore that. Okay. Now there are 3 model fit indices. Okay. There are 3 model fit indices that you will report. Okay, just like we have R square in regression, in SEM we talked about chi-square, degree of freedom, okay, GFI, all of those indices. In MLM, you have 3 indices that are reported. AIC is called as Akaike information criteria, BIC is called as Bayesian information criteria, and log likelihood is log like is essentially short form of log likelihood. Okay, now the smaller the AIC and BIC, the better is your model fit. Okay, there is no threshold. For example, in when we were doing, just like R squared, there is no threshold. Similarly, AIC, BIC, there is no threshold. The only thing is, the smaller the AIC, the smaller the BIC, the better is your model fit. So we want to reduce these, just like in SEM, people who are familiar, we said we should reduuse chi-square. Here we are saying we should reduce AIC, we should reduce BIC. That is a test of our model. And if you multiply this log likelihood with -2, it is called as deviance of the model. Okay, so if I say, let me write it on my whiteboard. So we say model fit AIC, BIC. Okay, the smaller, the better. Right? And then we say -2 times the third index is what we call as deviance of the model, is nothing but -2 times log likelihood, which is reported. Okay, and again, the smaller the deviance, better is the model. So we want deviance to be smaller, AIC to be smaller, BIC. We can compare delta deviance, okay, of, let's say, deviance of model 1, difference deviance of, so if you have 2 models, you can compare which is a good model by taking the delta deviance, okay, and we know this follows delta D follows a chi-square distribution. So we can test whether if your H naught is chi-square is equal to 0 and H1 chi-square is greater than 0. It means your deviance or delta D is equal to 0 or delta D is greater than 0. If delta D is 0, then you conclude that your models are same. If it is greater, you say models are different. And which would be a better model? The better model is one with smaller deviance. That is my better model. So that is what I say as so there are these three fit indices that we will keep in mind: the AIC, the BIC, and the deviance of our model. Okay, so that is what we have got.
Sir,
Yes,
sir,
yes, go ahead.
yeah, sir. So this is the one so this is one. So in our case, in organizational behavior, so there are multiple. So there are scales where there are multiple items. So how will this code change in that case, sir?
So when you will have multiple items, you will have to, uh, if you have multiple items, you will have to again average them or aggregate them and bring them to one value.
Okay, so average will do.
Average
Uh,
will do, okay. Or how I do it, I basically do the latent factor analysis in SEM, and I predict or write back the estimated latent factor value. So it is a more accurate, you can say, latent, the true latent factor value. So you get one value for all the items, right? That is the latent factor value which has been written back. So you
so
can either take the average of the items, or you can model the CFA and write back the latent factor value and then use that in your analysis. That is also fine. Just like in regression, remember, when we do regressions, we have to average, and if you have a multi-item scale, you have to bring it to one variable.
yes,
That
sir.
is exactly what we are talking about here. Because
Okay, so
remember, this
so
is
what you do?
regression, this is
What you
not
do?
SEM.
So what you do is you do a CFA and then you
Yeah, in
get
SEM,
a.
you can write back the latent factor values. Yeah,
Okay, sir. Okay.
it is possible. And then use
So,
that in your analysis. Yeah.
so you did mention about the restricted maximum likelihood, and you said that we should ignore that. But I've been using this maximum likelihood ratio in couple of other things. So it'll help if you can just quickly explain what
Actually,
exactly does this mean.
yeah. So restricted maximum likelihood is only working to reduce the variance in the data.
Okay.
Okay. Whereas maximum likelihood is working to reduce the variance or estimate your predictors, so that variance between, you can say, or the deviance between the estimated values and the predicted values is reduced. But in addition, it also wants to improve the coefficients of the regression. Okay,
Okay.
regression coefficients. But in restricted maximum likelihood, you are telling the software, do not bother about the coefficients, just try to reduce the variance that you are getting. Now that is why it is called as restrictive,
Hmm.
because you are not focusing on one. But when we will, so you should also not compare REML when
Hmm.
you are, you should not estimate using REML when you are comparing models. Okay, REML should not be used, maximum likelihood should be
Should
used.
be
So
used.
when we will start comparing the models, we will not use, or we should not use REML. It is said you should estimate it using normal maximum likelihood only.
Got
Yeah,
it,
I
sir.
have
That
done
answers my
this.
point because that would have been my next question. Yeah.
Yeah,
Yeah.
so
Okay.
so when we have to compare, like I just told, that we will compare whether our random intercept model is better than null model
Right.
by estimating the chi-square and the delta deviance, then we will have to use
Use the
the
maximum
maximum
likelihood.
likelihood and
Sure.
not the.
Got it, sir. Thank you.
Okay, so we have these AIC, BIC log likelihood. Now let's come to the random effect. Now you see there are two, it says intercept and residual. Okay, this is the random effect associated with intercept. So what is this? This is what? U0j or Rij? Intercept. It is the random
U0J.
effect associated with intercept is
U0J.
U0j. Very good. And residual is
Rij.
Rij, right? And what has it written? It has written standard deviation. So if we were to read the output, what is this output telling us? This is sigma U0, 3.26, and this is sigma R.
R.
Okay, that is what we have got. Now, when we were to compute AIC and BIC, sorry, ICC,
ICC.
ICC1, I told you, you should have sigma U0 square divided by sigma U0 square plus sigma
R
R
square.
square. So we will have to square these. That will give us the variance of U0. The square of 8.15 will give us the variance of sigma R or the residual, right? So that is what we will do. Now comes the fixed effect. You see, math regressed on 1. And the intercept value is 57.67. The standard error is this, the degree of freedom is this, the t value or the t stat, and it is highly significant, p less than 0.0001, whatever you want to say. Now what is the interpretation of this? What is this?
Gamma
Can you
00.
tell?
Gamma 00.
Gamma 00. Very good, very good. This fixed effect of the intercept is nothing but gamma 00. And what is the interpretation of gamma 00?
It is the fixed or overall
Overall
mean.
mean.
Overall mean, absolutely. So if I say mean of school dollar math, right? If I say I take the overall mean, you see it is almost the same. It is almost the same. 57.67, about 57 point. So if I take the overall mean, this is what it is giving us. Okay, and gamma 00 is nothing but the, you can say, an estimate of the overall mean, and it is highly significant, so it is significantly different from 0. And then these are residuals, the Rij within groups. So minimum, okay, then quartile 1, median, quartile 3, and maximum. So the Rij varies from -3 to max 5.29. There are 6,871 groups, 419 groups. Is this making sense, everybody? Is this okay? The output. Okay, now there is another command, line number 10, which says variance covariance. So it, what does this do? It just does nothing but it reports what is the standard deviation, and it takes the square of 3.26. The square is 10.64. 8.157, the square is 66.51. So what is our ICC1 is nothing but what we have got 10.6422. Let me correct this, 6.2.64223 divided by 10.64223 whole divided by plus 66.55130. And if I report this and I say what is my ICC null model, my ICC is, if you just select this variable name and run, it will give you the value of this variable. What is the who will interpret this number for me? Anybody? Anybody?
So that means that about 13.7% is explained by the 13.7% of variation in math is explained by uh, the groups,
That means
Explained
you
by
the
can,
schools,
yes,
schools.
the
schools,
schools.
right?
Yeah,
That means you can say that 13.78% variation in the maths
math
performance of
performance.
students
Yeah, yeah,
is because of school level
school level.
effects, school
Yeah,
level variables. Remaining, you can say 86% variation is because of individual whatever variables. The school has an impact of as much as 14% on the. Now it is up to us whether we say this is non-significant and therefore I am not bothered about what's happening at the school level, or you can say it is significant so I am bothered about what's happening at the school level. Okay, and therefore I want to the bring in the, you can say, the school level variables. So as I told you yesterday in our first discussion, we say anything above 10% is a good, you can say, variation to explain. Okay, so it is above 10. And but I also told you yesterday that there is no threshold for ICC1. Okay, that is something that we have to remember. Is this okay, everybody? Right, then you can also compute this using ICC1 can be very simply computed using the ANOVA command in our AOV, and it says math and it varies per school. So this is how ANOVA is written. So math varies per school. So as dot factor school code, data is school. So I run this and it is running line number 13, and I simply say ICC1 tmod, and so you can see it has computed ICC1, which is close to what we had got, about the same. It says 13.77% variation, and there is ICC2, it says 0.72. Okay, what does ICC2 say? ICC2, and I am writing the explanation on the screen, okay, and then we will discuss. It says the means of whatever variable we are interested in. In this case, we are interested in the math variable. The means of the variable reliably differ between groups. And in this case, what are the groups? Are our schools. That means the mean of the math score for group 1 is different for group 2, for group 3, and so on. Okay, so that means the math performance, this was the variable that we were interested in. The means of the variable reliably differ. That means they are significantly different between groups, and the convention is, let me say, the convention is 0.70. ICC2 should be just like reliability, right? We say greater than. So you can say this is within group, a kind of an estimate of within group agreement.
Sir, what is this T mod doing for ICC1? Because ICC1 can like you have divided the numbers, so ICC1 would have come as same only, right? So is it any adding to something for the T mod in ICC1?
ICC, no, this is so what we have done, that ANOVA stores the output of the ANOVA command is stored in tmod,
Okay, but
right?
I am asking that is that was that necessary for ICC1, because ICC1 would have come the same
Yes,
like
from this also, but
yes.
it gives us, this also gives us ICC2.
Okay, okay, got it, sir.
Yeah, so let me just take you to, I had it and I will cover, yeah,
So
group.
ICC1 is between groups and ICC2 is within groups.
No, let me just, so can you see the screen?
Yes, sir.
Yeah. So grouping statistics, ICC1 and ICC2, this is the command. So when you do ANOVA, you can compute easily both ICC1 and ICC2. What is the formula of ICC1? It says mean sum of squares between groups minus sum of squares within groups divided by MSB plus K minus 1 into MSW, that is sum of squares within, sum of squares with between, and K is nothing but the average group size. So ANOVA command one was, I was telling you, sigma u0, sigma square u0 divided by sigma square u0 plus sigma square r. But ANOVA can also help us break down the variance between and variance within, within groups and variance between groups. So this is the formula it is using when we do ANOVA, and that is why you see there is a slight difference. There is a slight difference between the values that we were getting, right? You see, when we reported ICC1 using this formula that we had done, we got 0.1378, and when we did ANOVA, we got similar, it was slightly different,
Yes, sir.
13.7, right? So it applies, Pratik, this formula. And ICC2 is very simply, this is very easy to understand. This formula is very easy to understand. It says MSB minus MSW divided by MSB, right? What if you simplify, it will become 1 minus MSW by MSB, right? Let me write it. Let me not complicate things here. Let me just open my, why is the whiteboard not working? Let me start it again. Just give me a minute, let it start. Okay. Okay, it will open up. So let me go back to the presentation. Once it opens, I'll let you know. So if it will become one, so MS, and we said ICC2 should be 0.7. Okay. If you simplify this, what will it become? It will become that the difference, okay, 1 minus MSW, that is the within group variance. Okay, it has started. So now let me write the equation and explain it to you. So what are we saying? We are saying ICC2 is equal to MSB. This is a very simple way to understand ICC2 divided by MSB. If we simplify, what will this become? 1 minus MSW by MSB. Okay, and let's say I said that ICC2 should be 0.7. Okay, so if we simplify this, what will it become? MSW by MSB is equal to 1 minus 0.70, which is equal to 0.30. So we can say that MSW should be 0.30 times MSB. And if I say if this increases should be greater than, then we are saying that it should be less than equal to 0.30 times MSB. Do you agree with this, Pratik? Okay. If we simplify this,
Yes, sir.
yeah.
Yes, sir.
So what are we saying? That ICC2 is telling us that within group variance should not be more than 0.3 or 30% of the between group variance. So between group variance can be large, but within group variance should not be more than 30% of the between group variance, which is essentially telling us that there is within group agreement, that within group, this is clustering, right? This is an estimate of clustering,
Yes, sir.
what we have been talking about, that within group variance should be less than 30% of between group variance. Do you agree with this interpretation?
Yes, sir.
So what
Yes,
are we
sir.
saying? That the responses of people, that means the maths group within school 1 are more similar than between groups. What is between group? Between school 1, between school 2, between school 3, between school 4 up till between school number 419. Right? That means the math scores of students reliably differ. They are significantly different from one school to the other. That is what ICC2 is telling us. That is why we say these are indices of within group agreement kind of a thing. Within group agreement. For ICC1, it's a slightly complicated formula. So I will recommend that for ICC1, you stick with this formula. This is very simple to understand, which is sigma square U0 divided by sigma square U0 plus sigma square R. For ICC2, this is a very nice formula that we should keep in mind when we are understanding what is meant by ICC2. Is that okay?
Got it.
Making sense?
Yes, sir.
Yeah?
Got it.
Okay, let us come back. So this comes from running the ANOVA command. And the added advantage is that the ANOVA command will also give you another estimate when it runs ICC. When we run ANOVA command, we get ICC2 and you get another estimate of ICC1. Fine, this is okay. So this is what we have. So this is what we have written. We have got an estimate. Now I have given you another command. Well, these are all different ways. There is one more G mean reliability, group mean reliability. So if you run this, it will give you another estimate of ICC. This is another. So there could be many functions. Okay, don't bother about it. I think gmean, for this we may need another package also. Let me just check what is the package. So if you just do gmean, what happened? Gmean rel. Okay, it is. So I will check. There is gmean. Yeah, and NLME package. So for this we may need to install another package. So for the time being, let us ignore everybody. We can, otherwise we will have to install another package as well. So we can leave this. You can stay with this or the ANOVA method. Okay. Now let us look at this. Very interesting. If we, yeah, there were some comments in the chat. Let me take them also. So Bhavna is asking, should we stop at this level if ICC is less than 10? Bhavna, there is no clear-cut answer to this question. It is up to you. Yes, you can stop. You can say that it is only 10%, less than 10%. Okay, and I don't think it's a significant variance. So I will not do any multi-level analysis. So if your ICC 1 is coming less than 10%, you can make that argument. You can say it's not significant, it is not too much, and I decide it is not worth the effort for deciding to go for complex multi-level analysis. So we can stop there. But you can also do it. Nobody is stopping you. So that is, can we get access? Yes, I will share. Yesterday I had not shared. I will put the PDF of the slides so you can refer to that also.
Sir,
Yes.
sir, I have a slightly general question because this is my first year into PhD and I'm not much aware. I thought like SPSS would suffice to do, most of the uh, things that we need to do for analysis. So, like, number one is are necessary. Do we need to learn uh, doing in this also?
Um, how do I say this? So, I would say that it is like saying that I can write with a pilot pen very well. So, should I learn to write or should I use an ink pen also? Or you can say I can write with a ball pen very well. So, should I use an ink pen also or a pilot pen also? It is your choice. It is your choice. The beauty of R is that it can do complex analysis very simply. It is a free software. You don't have to spend even a single rupee. At places, it is even more, you can say, graceful while doing analysis. Okay, and so ICC1 SPSS has no command to compute ICC1.
Oh,
ICC1
okay.
and ICC2 you cannot compute in SPSS. Okay, it has no way to give you ICC1 and ICC2. Okay, so we can do null model estimation. We can compute this and we can compute ICC1 like this. It is possible. Okay, but it cannot compute ICC2. So you will have to do it by hand. But in R, just one click, very simple statement, ANOVA, math, and it produced you all the results. So at places, Nivedita, I would say that just like you are learning to learn SPSS and doing analysis on SPSS, why not also learn to learn R? and do.
Sure, sir, because I wasn't aware how whether it is necessary or
It
not
is, it
necessary,
is,
or
it
how
is,
it is different from
yeah, it
SPSS.
is. First of all, tomorrow SPSS may launch version 28, or I don't know what's the current version, or 20, 30 and 32 and whatever, and you are working on SPSS 24. So you will think, let me buy SPSS 30 also. So you will have to spend money. At the moment you are in a institution which can fund you or which may buy a license for you and you can do it. But if you go out of the institute, you will have to keep buying newer versions of softwares and etc. For
Right.
this, for doing all this analysis, not even a single rupee is needed. Okay?
Understood, sir.
Yes, Pavan.
So basically, any multivariate linear regressions,
Hmm.
we generally interpret fixed effects, right? The
We can
we j-
estimate.
we we estimate fixed effects.
Yeah, yeah.
The reason we are introducing random effects here, I mean, just to interpret the impact of clustering or something. So in this case, do we always need to interpret the variances also, the random effect variances?
Yes, not necessarily all the time, but
I mean,
uh,
at least to report in the research papers.
yes. So yes, you will report. So for example, you will report what are the variances of U0J. See, this is the starting variance. Okay,
Right, yeah.
this is the starting variance. Then, as I was telling when Kanika asked that question, you will say initial U0J was 10, right?
Right.
When I bring my L2 and L2 variables, can I have I how much have I reduced 10? So have I brought 10 down to say 2? That means 8% variance that was there at level 2, I have been able to account using what?
Level 2 variable.
Level 2 variables. So that is
Right.
in a way saying that by adding these L2 variables, I have been able to explain the variance that was there at L2 initially, which was 10. Their means were differing so much. I have been able to estimate 8 out of 10.
Okay. Yeah.
So that is a way you can say. So we call this as pseudo R square, pseudo R square. So it is giving you an estimate of how much variance have you explained from the initial variance that was there. So variance explained essentially. This
Okay.
is this sum, you see 10.64 plus 66.55 is giving you an estimate of the initial variance, right? That exists
Right. Yeah.
in the null
Yeah.
model. Now
Right.
there are no predictors. We will check how much have we reduced this from the initial. That is giving us an estimate of how good is my multi-level model actually.
Reduce in the sense you're suggesting how much the level 2 variables able to explain
Explain.
the
So
variation.
that means this should go down, right?
Right. Yeah.
U0
Yeah.
square, sigma square U0 should go down
Right. Yeah.
because you have now, just like we say, initial residual is this much. If I bring in predictor, then they will account for some variance, right?
Right. So,
So this residual should go down essentially. Ideally, it should go down to 0. That means I have perfectly predicted my math outcome,
yeah.
correct?
Sure.
So that is giving us an estimate of what, how much have I explained out of this.
Okay.
And
Thank you, sir.
how are you explaining? By bringing in L1. L1 will estimate this, L1 will
Right.
estimate 66.55 and L2 will estimate some variance from 10.64.
Yeah.
Getting this?
Sure. Sir. Yeah.
Yeah? Okay.
Yes.
Chalo, let us go to line number 24 now. Okay. What have I written? I have written determining if tau 00 is significant. Okay. And what have I done? Now I have done simple regression. So it is generalized, general least square, okay, model. And what have I done? I have said math regressed on 1. data is cool, and I have again said control the same optimization function, opt is equal to optim. Okay, and let's run line number 24, null model 2. Sorry. Okay, and then I will compare null model with null model 2, right, by comparing their deviances. And the command is very simple, very simple. Look at the beauty of this language. Just one command, ANOVA, the null model that we had estimated, the multi-level model, and null model dot 2, which is the model where we are not modeling multi-level, we are modeling simple linear regression. Okay, I do this, run this command. Okay, and what do I get? Null model and null model dot 2. Okay, so this is model 1, model 2, degree of freedom 3. Now you see AIC, BIC, log likelihood. Which is a better model? AIC is smaller for null model, BIC is smaller, it is higher for model null model 2, which was our single variable regression. And then what is the difference between these? You multiply it with -2, you get this chi-square, log likelihood ratio. Okay, 483. So let me show it to you. Calculator, let us open the calculator. So I say minus 24438.66 minus parenthesis minus 24680.58. Okay, you get divided, no, it should be 24680.58 minus 24438.66. Okay, and you multiply it with 2, 483.84. You see what is this, is what we are getting. I have ignored the minus because we will anyways multiply it with -2. So this is the difference in the deviance, and this is your chi-square. And is it significant for what is the delta DF? Delta DF is 1. So it is highly significant at p less than 0.001. That means these two models, what is the interpretation? These two models significantly differ. And which is a better model? Tell me which is a better model, everybody.
Null model.
Huh?
Null model.
Null model. The model that has a lower AIC, BIC and log likelihood is a better model. That means what are we saying? That rather than modeling it as one level and estimating one regression line, it is better to estimate it as a multi-level model. That is telling us that this model is actually better. Is this okay? Making sense? Yeah? Okay. Let us go to now model number 2. You see line number 27. Yes, Deepak. Which is
Sir,
random intercept model. Huh.
actually, I have doubt that in normal regression, we always have a predictor variables. So
Yeah.
what software is doing here without predictor variable and still finding some coefficient using the
So what is
regression?
it? It is nothing but estimating. It is estimating the regressing it on a intercept. What does that mean?
Okay, understood.
Estimating.
Only intercept.
Yeah, it is only estimating the mean.
So there are what I was thinking is there are only intercepts, then only constants are there. Actually, in regression we
Constants.
have
Yes.
predictors which have certain variation. So actually,
Yes.
what is that? So here also it is taking the variation of intercept
Yes.
and then
Yes.
regressing it on the.
Yes. It is
Okay.
just estimating the intercept here.
Okay.
There is no predictor here.
Okay.
So
Yes.
So between model 1 and model 2, the null model and model dot 2, the only difference is the LME and the GLS. Is that correct?
No, we removed the random also, right? We said there is nothing random here. It is just one level regression.
Right. Okay. Okay. Got it. Yeah. Yeah. Yeah.
Yeah,
Okay.
see, if I show you the summary of null, what is it that I have written? Null dot model dot 2. Yeah, you see, this is generalized least square fit, okay, AIC, BIC, and then you get this. There is, you see, there is nothing random here. This
Got
output
it.
is missing. The
Yes. Got it.
randomness, random effects are missing.
Right, sir. Thank you.
Hmm? Okay. Okay. Now let us do random intercept, and we are running out of time, so we'll just do this one, and then we'll come back and do this. Tomorrow we'll go a little faster. So now what am I doing? I am doing, now we did step 1, we computed all our indices, we come to random intercept. And what did I say? I said math ij is equal to beta 0j. Now I bring in my SES ij plus Rij, and I say very simple model that I am running. I will say it is gamma 00 plus U0j, and beta 1j is a constant. So what will it become? It will become, the multi-level math equation will become gamma 00 gamma 11 SES ij plus U0j plus Rij. So there are two fixed effects now. There are two random effects now. Random effects. So what will be my command in R? It will say math is regressed on. This is anyways coefficient is 1, so I will say 1 plus SES, right? Because I have brought in the SES variable in the regression now, comma, random is equal to tilt. It is still, there is no random slope, there is just random intercept, so it will be 1, and it varies for school code, and then simply data is equal to, very simple. This is my command. The fixed effect, remember the formula, the syntax is fixed effects comma random effects. That's it. That is all that we have to do, and this is anyways what is the data on which analysis has to happen. Okay, so this is what I have written here. Let's call it as model 1. This is what I have written, model 1. I have said LME, linear mixed effects. Math is regressed on 1 plus SES. This is the fixed effect declaration. 1 plus SES. Random is equal to tilt 1, and it varies per school code. Data is equal to school, and this anyways you don't have to bother. So this is very simply the command. Very simple. Let us run this. It has run, and do the summary. What has happened to AIC? It has become 48223. Okay, and if we see what was our null model AIC, you see here this was the null model 48883. Okay, 48903. What has happened to our AIC and BIC? So by looking at AIC and BIC, which is a better model? Tell me.
This is a better one.
Our random intercept model is a better model. That
Better
is
one.
what the
Better
fit
model.
indices are telling us. Now you see, everybody, look at what has happened to our U0J standard deviation. What was it initially? Initially it was 3.26 standard deviation. Now it has gone down to 1.86, right? And 7.925. That means Rij has also reduced because we have added a level 1 predictor. Okay, this is the what. Now look at the fixed effects. This is now telling us the intercept, and this is the coefficient of SES, and it is highly significant. What does this mean? What does this mean? The coefficient interpretation, because it is Z, so one standard deviation change in SES, it changes maths performance by 3.87 marks. That means there is a positive relationship between maths performance and SES, socioeconomic status of the student. That is what we are seeing. There is a significant relationship for every one standard deviation change in socioeconomic status of a student. His or her maths performance goes up by 3.87 marks. That's the fixed effect that we have uncovered. And then there are residuals that are reported. Okay, and if we compare this, okay, let me just do variance covariance, where core null dot model. Okay, this was initially in the null model. The variance in the intercept was this much, residual it was this much. Let us report for model 1, model dot 1. What has happened? The variance in the intercept has gone down by, from 10 it has gone down to 3.46, and residual it has gone down from 66 to 62.809. So you can say reduction, this is what I have written here, reduction in variance within schools, within school, not between school. It is nothing but 66.51, which was initially 551, minus 62.809 whole divided. So this is the percent, you can say this is the variance explained by bringing in SES. 5.6% variance explained, and the reduction in variance between school, you can say, is 67.4%. Now that means after bringing in a L1 predictor, I can now see that the variation in the intercepts between schools has also gone down by as much as 67%. It has gone down by so much. Okay, and again, if you want to, but this is not so much needed. In ICC1, you can say now there is 5, even after accounting for SES, okay, there is still 5.23% variation that is unexplained in the intercept, and that is perhaps something that I want to bring in. That is something that I want to explain or think about, and I would like to check it with my L2 predictors that I have. Is that okay? Is this making sense? Any question here? If not, let us do this model number 3, and this is the last one, and then we will stop. Let me share my screen again. Now we bring in our 3 predictors, right? So now this was our model. Now we want to bring in gamma 01, W1J, gamma 02, W2J, and gamma 03, W3J. So what will it become? Gamma 00, gamma 11 SES IJ plus gamma. So what will it become? Let me write it here. Plus gamma 01 W1J, or this will be SES mean J, gamma 02 pro 4-year college J, gamma 03 public J plus U0J. So how many fixed effects now? 1, 2, 3, 4, and 5. So there will be now 5 fixed effects. So what will this become? The command will become, let us erase this. The command will now become, okay, the command is now going to become 1 plus SES mean plus pro 4-year college plus public comma random is equal to tilde continues to be 1 school code comma data is equal to school. So 1, 2, 3, 4, and 5 fixed effects, right? And if you see, this is the command that I have written here. LME maths is regressed on 1 plus SES mean pro 4-year public. Random is 1, varies per school code, data is school. If I do this now and then report the summary, now you see what have we got. Our AIC has gone down. Further, let us compare it with what we had. It was 48223. It has gone down to 48143. Okay, and so on. Our variances of intercept and residual, not so much in residual, but intercept has gone down. And look at what has happened now. SES significant, SES mean significant. Now you see, for every 1 standard deviation change in SES mean, the math score improves by 2.47. That means schools that are richer, or schools that cater to richer children, on an average, their maths performance is higher by 2.5 marks. Pro 4-year college, on schools, every 1 standard deviation change in pro 4-year college changes the maths performance by 1.41. That means what? Schools where there are more students who want to get into university, 4-year university, they tend to study harder maybe, and their maths performance is better by 1.41 for every 1 standard deviation change in pro 4-year college. Public and private, there is no significant difference. Whether it's a public school or a private school doesn't matter, right? And you see, we can compare this model with the previous model where we had not included L2 predictors, and you see here there is a significant difference, and which is a better model, which has a lower AIC. Okay, though it is giving that it may not be very meaningful, but we can still see that there is, and model 2 has a lower AIC and lower BIC. Is this okay? Any questions, anybody? Okay, if not, let us take a pause here and we'll come back tomorrow at 3 o'clock and continue this discussion. Okay.
Yes, sir. It's very heavy, so it will take some time to.
Yes, yes, yes. So go back, take a look, go through the recordings and just practice it before we meet tomorrow, right? And think about any questions you may have. We'll take them tomorrow. Yes, Pavan.
So for this model one, uh, in the random effects, can you please help me interpreting that standard deviation part?
Standard deviation. So what has happened to standard deviation? You tell me. Variance covariance. Let's do it here. And what was variance covariance of model 1? It was this. Now you see what has happened, Pavan. See, the residual variance has almost been the same. Actually, it has
Right.
slightly increased, but it is okay. And it has decreased a bit. It was 62.80. It has now become 62.63, right?
Yes.
And
Yeah.
which is expected also because we had not added any L1 variable, correct?
Right, sir.
Right? Now, what has happened to the variance that we had at L1 level,
Hmm.
L2 level, the variance was 3.44 previously,
Right, sir.
right? And in
Yes.
null model, it was 10 actually, right? Let me also do null
Yeah.
model, right? It was 10
Yes.
in the null
Right.
model.
Huh.
When
Yes.
now that we have added the L2 predictors, where have we reached? L2 and L1 predictors, we have reached 2. How much
2.
have you reduced the variance? There is still some variance that is left in terms of their difference in means, but we have been able to explain the difference of 10.64 minus 2.399. That is what we have been able to explain.
Explained. Right, sir.
Correct? That is what I
Yeah.
have written here. You see, reduction in variance, line number 47, reduction in variance between schools.
Yeah. Yeah.
Because we have added these variables, and reduction in variance within schools by adding all these predictors from 66.551, we have gone down to 62.63.
Right, sir.
That's the percent variance explained, and that's the percent variance explained between schools. So you can
Right.
say that I have been able to explain 77% of variance that was at level 2 by bringing in
Okay.
these. Well, yes, there continues to be 36% or 33%, no, sorry, 23% variance still, which is okay. But my model can explain that these three variables can explain 77% variance that was there at the school level.
Okay. Understood. So, but in a general scenario, let's say I'm not comparing the models. So basically, I'm not comparing my model with any null model or any random intercept model. I'm directly using a random coefficient model for that matter. So in that scenario, we are not, we won't be able to explain the
Yeah, so it
reduction
is
in
okay. See,
variances, right?
these are all additional things that you can do. I am saying this
Right,
is all additional that you can do.
right.
But for sure, what is important for you is now that you have been able to delineate what is the effect of L1 predictor.
Right, yeah.
Now you can say that for every rich school that
Mhm.
changes by one standard deviation, you are jacking up the marks by 2.5, which is
Yeah.
understood. Richer schools maybe cater to better students, maybe they have better parenting, whatever, and their
Yeah.
performance is higher by 2.5 marks. Every school which is preparing, which has more percentage of students who want to go to university, maybe they
Mhm.
study hard and their maths performance is therefore higher by 1.41 marks for one standard deviation change.
Yeah. And this is basically the fixed part. So we can also make an addition and explain, but there is existent variation among the, sorry, between the schools, and
Yes,
the following the
yes,
variation might
and I
explain
have
that
been
part.
able to explain 77% of the variation that
Exactly.
was earlier there.
Yeah, yeah.
There is still
Understood,
some
sir.
variation which will always, in a regression, that is what happens, right? Residual always remains.
Right, sir.
But here I have been able to explain this much
Sure,
through
sir.
my L1 and L2 predictors that I have brought in my model.
Models. Okay, sir. Thank you so much.
Yeah.
Yes.
Chalo, let's stop. Okay, thank you. And I will upload the recordings and I will also upload the presentation today so you can see it, and I'll see you all tomorrow. Thank you.
Thank you
Thank
very
you.